So thanks for having me. And so I like to talk about embracing approximations in reinforcement learning as a response to Rich's talk. So Rich was kind enough to share his slides with me, so I'm going to recycle some of the slides, and I will try to convey the perspective of a person who's been working on the theory of reinforcement learning since for a while. So let's get started. But before we start, let's wish happy birthday for Roshan. I think today is Roshan's birthday. I don't know whether Roshan you're here, but if you're here, happy birthday and thanks for being with us. Thanks for being such a nice student, nice person in general. I'm going to talk about a result that is joint with Roshan. I will briefly mention, to be precise, that result, and maybe in the future, in some future tea time talk, Roshan can elaborate a little bit on that result. Okay, good. So lots of people wishing happy birthday to Roshan. Here's the contents. Yeah, Monday, more details. So here's the contents of the talk. Why do we need approximations? Is scaling with computation really new? So that was one particular point that Rich was emphasizing, that we need to switch to a new view in computing science, scaling with computation. So I want to elaborate on that a little bit, what has been done so far, and what is missing. And then Rich also talked a lot about that we need to abandon a lot of things. It was pretty scary, to be frank. So I'm going to go through some of those things, and I'm going to give you my view of like what needs to be abandoned, and then some brief outlook, maybe two other things. So the necessity of approximations. I think that this must go back at least to Bellman. So as far as I know from biographies written about Bellman, he was a mathematician that wanted to solve like everything in closed form, in analytic closed form solutions. So he left PDEs. That was his background. So he just wanted to have all these solutions. And then very soon he realized that that's not going to work. And then he started to drift towards developing approximation techniques, approximate computation techniques. I'm not sure whether he liked those or not. Few biography writers of Bellman say that he really hated those. He really wanted to have the exact solutions. But so this expression, curse of dimensionality, in particular goes back to Bellman. And it's worthwhile to reiterate what he, in our interpretation, or my interpretation, I don't know, after like, I don't know, many, many years later, just reading his works, what he might meant about this. I think what he meant about this is that for any reasonable problem that you might be interested in solving in optimal control and related problems, you're going to have many state variables. And when you have many state variables, even if the state variables, like you will have to work with a space that can be described with variables with many components, to be precise. Okay. And you will have many components. And even if every component just takes on two values, if you have d such components, you will have 2 to the d exponentially many in d possible values. So if you have a method that relies on enumerating all of these possibilities and then going through them even only once, then you'll be doomed. So that's the curse of dimensionality, as far as I understand from my readings. So in other words, if we are in the MDP framework, you have a state space, and that is huge because it has this, oftentimes in applications, this multi-dimensional nature. And the action space is similarly huge. And you can't afford even polynomial time computations in the size of the state and the action spaces. Okay, so that's what the curse of dimension refers to. And to drive that point home, we could cite a theorem, for example, that goes back to Christos Papadimitriou and John Titiklis from the 80s, where they really go after whether it's really true that if you have an MDP, then you have to look at every single state and action at least once in order to come up with the optimal policy. And the answer is yes, you have to do that. So unless you do something else, you're doomed, okay? So this seems to be like it's a no-go if you want these exact calculations for all possible MDPs of interest. It's just a no-go. So approximations are really, really necessary. So Rich was emphasizing that, okay, approximations are necessary, that it has been realized quite early, but maybe what's new is that you need to scale with computation, which is not, like he emphasized, that it's not the usual thing in CS. So he was saying that the usual scaling is with the problem size in CS, and the standard CS results look at exact solutions and the time needed for exact solutions. And the new scaling is with computation. And what we want is that we want, with more computation, a better approximate answer. And we might not hope that we will ever be able to calculate an exact answer. Okay. And so the question is whether, is this really new, right? Because like, early on, I would say, in computing science, it was realized that most of the problems we are interested in, it's kind of the same story as with Bellman. The most of the problems that we are interested in, we can't solve them exactly. So I would say very early on, people realized that this, like the scaling is just done, it's not going to cut it. Like we need to do something else. And so that was, that gave birth to this field that's called the field of approximation algorithms in theoretical computer science. And so beyond that, there is also a very rich history in RL and also bordering field of approximation algorithms. And so I'm going to talk a little bit about this, these two subtopics. So what are these approximation algorithms? So Wikipedia says this: approximation algorithms are efficient algorithms that find approximate solutions to optimization problems, in particular NP-hard problems. Well, I'm not sure whether you need that parenthetical expression. Maybe it's like other problems. With provable guarantees on the distance of the return solution to the optimal one. So there are some points of this are a good fit to what Rich was talking about. But some of the points are not really a good fit. So to elaborate on this, so let's think about the typical result, typical approximation theory result. How does it look like? The typical approximation theory result, at least this PTS approximation results, they look like as follows. You have a scalable family of algorithms, if you wish. The algorithm takes as input an epsilon, and it's going to take 1 over epsilon time, or a polynomial function of 1 over epsilon. And as epsilon gets smaller, it does more compute, and it produces a better solution. So in a way, like you can even turn this around, and you could say that, well, okay, this is just another way of saying that after n steps, you're going to have a 1 over n access loss over the optimal solution. Sometimes it's a multiplicative access. Sometimes it's an additive access. More often than not, it's a multiplicative access. So this has pretty much all the elements I would say that Rich is looking for, right? Like you throw more compute at the problem, and your solutions are improving. So this is not really that new to people in CS. I'm not necessarily saying that in our field, this has been the common view, but definitely in theoretical computer science, this is kind of mainstream. And you might think also that, okay, maybe this is too much to demand that in the limit of infinite compute, you will get V star in efficient ways, sort of. And indeed, like you can find these works when you can get only a 2 approximation which means that you're losing a factor of 2 in your losses, in your access losses, and so on and so forth. So there are variations of this framework. So just to drive home how big is this field, if you enter in Google Scholar approximation algorithms, then it like just today, it brought up like 470,000 hits. I'm not sure whether all of this, like, I'm pretty sure that they are not all of this. But if you look at, like, there are books, and Randy was mentioning the 78 best books in approximation algorithms and so forth. It's a big field. Now, my claim is not that I know this field. I know it a little bit because it's obviously bordering with what we are trying to do. I won't even claim that I try to, check what type of results they have, and I wouldn't claim that you can just like go and grab some results and you can run with them in reinforcement learning and then you will get new and interesting results. I don't think that that's really true. Some of the tools could be useful. We're definitely borrowing more and more techniques from the theory community in CS, but it's not like that. Like these people have worked out everything, and then we just need to collect the fruits of what they have done over many years. Okay. So what are the approximation results then in RL that we have? Okay, so to talk about this in a meaningful way, we have to be a little bit more specific about what type of problem we want to solve in RL. And so I like to distinguish between 3 types of subproblems in RL: planning problems, batch reinforcement learning problems, and online RL problems. So in planning problems, you're interacting maybe with a simulator, and you want to come up with a good policy. In batch RL, someone saved them some data, and then you want to come up with a good policy. And in online RL, you're interacting with the environment, and as you go, you're collecting rewards. So that's like the real deal, and you want to maximize the reward that you're collecting. All right. So the first observation here is that maybe this Papadimitriou and Titiklis result is a bit of an overkill here, because no one actually needs to know the full optimal policy ever. I mean, not at all states. You only need to know it only at the current state. You always have some state. And then, like, okay, so maybe you say that states, like, you should stop mentioning states, will come to states. All right, so that's the next point. Like, can we talk about states? Like do these states exist? And like, why are we doing this? All right, so here we go. So this is about states. So here's my big theorem. It just says, without loss of generality, the state is observable. You have state. Don't worry about it. Okay? Just think about it. Like, we have state. Like, problem solved. Like, we talk a lot about like how to construct states, but we have state. It's not a problem. State is there. Okay, so how does this work? Well, it's super simple. So what is the context of this theorem? The context of the theorem is control stochastic systems. So what are control stochastic systems? These are systems where you're taking action, sending it to the environment, and you're receiving observations as a result. And the distribution for the next observation can depend on the past actions and the past observations. It's like the normal thing that you would want to do. Okay, so nothing special there, nothing to worry about. And I say that if you have a control, so this theorem says that if you have a control stochastic system, by definition, you have the state. Like, it's easy to construct a state. So what does it say? So what's a state? So a state is like, by state, we mean a Markov state. A Markov state summarizes the history for the purposes of predicting the future, so that you can forget about the whole of history, okay? And you will be able to predict the future if you have the Markov state in your hand. And of course, this big theorem is going to have this single line proof, which is that, well, as a state, you can just take all the past observations and all the past actions, and that's your state. Just take it. You can run with it. It's a Markov state. So when we're saying that you don't have a state, you have to observe the state, that makes no sense to me. As far as I'm concerned, you can easily get a state. So what's really the problem? So we have this little emoji there that shows that there is maybe some problem. But maybe it relates to some other problems that we usually have. So I think that we should accept that we do have state. There is no problem with constructing states, but we might still have the feeling that we are missing something a little bit. So you might criticize this construction by saying that, well, okay, the state variable has an increasing number of components, but like, I don't care. Like, why do you care about this? It's just a state. Like, I can, let's say all the observations are finitely many, and there are finitely many actions, then I can just like renumber everything, and I get a countable state space, right? So it's not a problem, right? So just the fact that we have an increasing number of components shouldn't bother anyone, I say. Maybe the problem is that we're going to have a lot of states, right? So that's really the problem. So what I'm trying to say here is that the problem is not that you don't have the state. You can have the state if you want to, but you will have many, many states. And now you have to like deal with that. But there we are circling back to what we started with, that we have to come into approximations anyways. So I say that state is not a problem. Let's just do the approximate things, okay? Let's just do the approximations. If you're doing a good job at approximations, you'll be done. Don't worry about mentioning states, relying on states. You have states. It's okay. Just don't use that you have a few states. Your algorithm are not supposed to use that, but it can use that you have a state. That's not a problem, right? Okay, so that was one important bit. Okay, so the next point is that, okay, in this construction, we immediately see that even if you started with finitely many different observations and finitely many different actions, you end up with a state space that's infinite. And so the question is like, is talking about a finite space MDP like what we do here? This is copied from the paper with Roshan that we just submitted to NeurIPS. Is this blasphemy? Is like, are we committing some kind of crime here? Is this a big problem? I say it's not a problem. Like, we do this for the sake of convenience. So whenever you read a theory paper, give those theorists a break, please. So what they write might not mean what they mean. So when I write, let's take a finite MDP, if I'm not using that I have a small number of states and actions, maybe I sneakily use some boundedness properties, but that's all, okay? So you have to be careful with this thing. So finite is fine. Actually, I learned this from Rich. Like, when I arrived in Alberta many, many years ago, I was all about continuous spaces. And he was like, Csaba, like, what are you doing? Wouldn't it be much simpler just to assume that you have a big finite MDP? Isn't that complex enough for you? And I was thinking about that at the time quite a bit, and then I quit the continuous MDP business. I quit it because it's easier to communicate the results with the big finite MDPs. And so I don't know whether Rich remembers this, but it had a big influence on how I communicate research, because I gave up on a lot of the measure theory blah blah that I was doing in the other days. Anyways, okay, so finite action spaces, is it the same deal? Maybe not. We can talk about that later. Okay. So how to plan in a big finite MDP? So maybe one of the problems is that you want to come up with a good plan. So the Zerus idea is that you have a simulator, because otherwise you would need to read the specification of the MDP. It would just take too much time. So you can't do this, right? So you have to have some kind of a simulator that you can send things to, and then you get responses from, like next states. So you send in states, like, or maybe you have a current state, right? So that leads to idea number 1. Idea number 2 shouldn't be there, but I couldn't like fix this animation. So idea number one is that you have a current state, and you only need to know how to act at that state. Like you never need to know how to act at states other than the current state. Like I've never heard about any problem where someone would really need to know how to act at all possible states simultaneously. It's impossible to even store any policy for that. I mean, like you could use approximations and whatnot, but like at the end of the day, when you need to execute this policy, you're going to be given a state. So just use that. And this was very early realized on that you don't, if you only need to have a good action at one state, then this is an easier problem because you can build a look-ahead tree. You don't have to, like there's the parts of the state space that there is no way you can get to in the lifetime of the agent or whatever. If you're using discounting, we'll talk about discounting a little bit later, maybe. Then there is an effective horizon, and then you only have to build a tree up to that point, and so forth. So that's the next idea. And if you have a simulator, you can just like enter this state, enter some action into it, and it returns next states from the underlying unknown distribution, or like the distribution that represents the environment, and then you can go on that way, right? So that's the framework you can use to do this approximate planning. And the next idea, which is independent of the previous ideas, is that maybe someone gives you a hint. So this is computation with a hint. And the hint is that, well, here are these features, and the optimal value function lies close to the span of these features. I kind of like this model. And it goes back to the work of Bellman and others, and in particular Schweitzer and Seidman. They really elaborated on this problem in the 80s. And I think that this is really goes to the heart of a lot of things that we do in reinforcement learning, this function approximation. We're betting on that some value function, let's say the optimal value function, or maybe just like the advantage function, and you can have variations of this, can be expressed in a compact form. And then you try to use that to come up with a good algorithm. And it's non-trivial to do that. And the guarantees that you need to have in this case is not like that. You always, for every MDP, you need to be able to compute really good actions no matter what. Well, if your features are bad, then no one can really do much about that. So you have this relaxed goal, this approximation goal, that if the features are not so great, then you're given a free pass. But there is no free pass if someone gives you good features. Okay, so that's the problem. And Bellman in particular, and Kalb and Kotkin came up with this idea in the 60s. So it was from the need of like, oh, we just want to compute these things. And then they were like, oh, we can combine polynomial approximations. At the time, it was not so general. So they were just talking about polynomials with dynamic programming or successive approximations type of algorithms. And then they were running experiments, and they were amazed how good the results were. And so look at their enthusiasm. They say, if we combine all these techniques with successive approximations, that's like value iteration or policy iteration, there should be very few allocation processes. So that's a specific MVP, which will resist our efforts. Like it's amazing. 63. Very, very optimistic. All right, so the Schweitzer and Seidman paper, I recommend everyone to take a look at it. I discovered it too late. It's from 85. It's a very nice paper. I mean, like mathematically, there is not much in it, but there are some of the founding ideas of the whole field of approximate dynamic programming are very clearly and cleanly presented in this paper. In particular, algorithms for linear programming and value iteration and policy iteration, LSPI and TD. It's all there. It's like buried. Like TD has a half a sentence that, oh, we could do this, and then that's it. And they left it like that. So in a way, it's unsatisfactory, but in other ways, it's satisfactory, or like it's pretty curious that they were doing this. Okay, so this leads to the next topic: approximate dynamic programming. So this is like a big topic in our field. So we have been doing approximations since the very beginning of the field. The number of references here is not that high. It's 800,000. But early on, people worked out theory. So maybe you can criticize the conditions under which that theory works. But here is a result from slides by Dimitri Bertsikos, and later on, Remy was refining these results to relax the conditions. Yeah, I won't go into the results. It's just like showing that like this idea that you need to do approximations and then you're mixing it with computing good policies has been around. There's been a lot of work on it. The type of results that you get are approximation type of results. So here the result says that, well, if your errors are smaller, then you get better. This is not talking about the amount of compute that you need to spend on this, but that's like you can add that corollary to this result. All right. So finally, we come to the result that we sent with Roshan together to NeurIPS 60 years later than this paper. So this uses approximate linear programming, and it has this like all the signs of a good approximation result. So kappa, 1 over kappa is the effort that you put in, the compute. If you are making kappa smaller, then you're gonna put more effort into computing. It's like the reverse thinking, but it's like you can make this an anytime algorithm that like any amount of resources you throw on it, it gets better. So kappa is one of the quantities. Epsilon is the other quantity. Epsilon is this quantity that describes how well the feature space captures the optimal value function and only optimal value function. And there are some curious quantities here, and there is discounting, and then you can ask me about discounting if we will have time for questions. But I need to get to the end of the talk, I guess, right? In online rel, I similarly claim that there are results. So I'm just showing, you know, I'm really biased towards results I've been working on. So this is joined with the main authors are Yassin and Nevena on this line of work. I talked about that, this line of work. This is a Smith specification, general function approximation. You're computing regret either relative to the best policy or policy in a class. So it's like there is a rich literature on approximation algorithms. Okay, so what to give up, what not to give up, finite MDPs, I don't think that you have to give up on those. But don't design algorithms that only work if you can enumerate all the states and actions. Doing analysis for that, I think that that's still fine if the purpose of the analysis is not to say that, I mean, all right, it's too much like that. Anyways, I don't have time. Sorry, I ran out of time. I really much agree with Rich on that you need to track. You need to forget, therefore you need to track. I think that we're making very good progress on this problem, especially in supervised learning. Not so much if you are combining with this exploration. It seems that in that case, that this problem is really hard. So in summary, I think that what we need is flexible methods that are able to deal with any sort of bias that you want to throw in, or hints. So computation with hints, any sort of hints. And you need algorithms that are able to do with many different forms of this. And these algorithms need to be scalable in the sense that Rich was also emphasizing. More compute, more interactions, better outcomes, up to the limit of how good the hint was. Like without the hint, we know that you can't do much. Right, so there is much left to be done, and some of the work is ongoing, and you can join the ML-theory Slack channel at Amii if you're interested in what's going on the theory side in our house. Okay, with that, I stop. Thanks.
Well, thank you, Csaba. We are slightly over time, so we'll just take a couple of questions before closing. So if you have a question, you can unmute and speak, or you can put it in the chat.
Okay, you can all hear me.
Yeah.
Of course, I enjoyed this very much, and a lot of good things were brought up and important work that we should know about. But I have to think that Csaba Csaba, you are largely still in denial. You're denying that there's a problem. So I guess the easy case would be is you are not accepting that the agent has to work with a non-Markov state representation, and you suggested that the history is always available and the history is Markov. And
can I say something?
Yeah.
I'm saying that if the agent wants to work with a Markov state, it has an option to work with a Markov state. I'm not saying that that would be a useful option. It is just like it's a finicky.
It's not a useful option, and so you're denying that we need to do something else by mentioning this useless option. So you really you have to work with a non-Markov state. I think.
All right.
How to say that? Number one is to remember the history. The history is the size of the world. It's effectively the size of the world. So just to hold the history in the agent's head, the history is larger than the agent. I would say that. And I would say that you have to. That's the discipline of accepting approximation, that you cannot remember even your whole history. But I want to go on. I want to make my second larger comment, and then I'll shut up. Okay. Which is to say that the thing about is the sense of approximation that I was trying to talk about, is it new? Well, I think what you said is oh no, well, you almost are missing the point, which is that I expressed it as the old kind of scaling is how long does it take you to find an exact solution? The exactness is not the important. The exactness is like classical computer science. But modern computer science, instead we say the time that it takes you to get within epsilon of the solution or something like that. And that's also not what we need. That's the old stuff. We have to get beyond the time to get within epsilon of optimal. And the easiest way to see that it's not what I'm looking for is that anything that expresses in terms of the optimal solution is irrelevant, in my opinion. You're not going to. I will not take seriously anything that says in the limit we will get the optimal solution. The optimal solution is totally irrelevant, and we need to look at. We have no idea where the optimal is, but as we invest more computer resources, we should get a better answer. That's what we're looking for, and that is new, I would claim. Thank you very much.
All right, Rich. Thank you. So I'd like to react just quickly to this, that whether I'm in denial for access to the state or Markov state. I don't think I'm denial. I'm just nitpicking on the terminology that is being used. Because if you say that there is no state, then it seems that like you're forbidden to use the word state, and like there's nothing like that. You can use. I think that a lot of people can get confused about whether there exists a state in the environment, whether a state is accessible to the agent, or whether it's useful for the agent to think in terms of the state that's accessible to it. These are different things. And I'm very much with you that I think it's a big problem if you very quickly converging on choosing a state representation, which by definition is Markov, and which gives you a small state space. I don't think that that's real. Like that doesn't happen ever. That's not really useful. So I didn't want to say that. So with this, I also would like to know that I flip back to this slide. So on this slide, I didn't have time to elaborate on, but so this algorithm just works entirely in the feature space. And maybe that's not super interesting for a planning algorithm. It is somewhat interesting still, right? So it doesn't have to have access to states, just the features of them. And you have this non-Markov property all over the place, and you have to deal with it in some way when you're in the feature space. And you can have online versions of algorithms like this that that similarly just work with the features of the states. And I think that this is an important property and important to design algorithms like that. Okay.
All right. Let's thank the speaker for an interesting discussion. And we'll see you guys tomorrow. Please tune in at the same time. And we have another couple of interesting talks for the week before our social on Friday. See you guys tomorrow. Thank you so much for attending.
Yeah, see you. I can stay. I will stay. I'm happy to take more questions if anyone. No one should feel obliged to stay.
I had a question in the chat. So, like, I'm not certain about whether this would be actually, necessary, but it's, interesting to consider about what ways we might measure our agents if we're forbidden from using a Platonic optimal policy true value function or information state.
Right. Rich was saying that if we're if our result says that compared to the optimal, like the ultimate optimal, like we're getting close to that's like a sign of like something weird is going on. And if you look at results, like what's on the slide here, so this result also, it's not like optimal is mentioned there, but compared to the optimal, there is an offset. And this offset is like shifting what you might hope to achieve even in the limit of infinite compute. If your hint is not good, so this epsilon governs this offset, okay? So if your hint is not good, you have no guarantee of getting any good results. And it's rightly so, because we have these lower bounds that say that, well, unless you're looking at all possible states and actions, and then there are just way too many of them, you can't get close to the optimum. And so these algorithms are making a stronger claim, some polynomial time claim, which is independent of the size of the state space. The only way you can do that is if you're relaxing of what you're comparing yourself with. So here you're comparing yourself with maybe some policy. So roughly you should imagine that you're comparing yourself with the policy that you could get if you were given all the knowledge about the MDP infinite compute, but you would be restricted to use to express your policy in terms of the features that you were given. Because you don't have access to the state, so you can't do much. You have to use the features. If you have that, like the optimal policy is not accessible to you. So compared to that policy, how well can we do? So roughly that's the sense that that you can get meaningful results. And I think that makes a lot of sense. Like people are trying to get these results.
Thanks. That actually really clears things up.
Okay, good.
Oh, and just as a sidebar, you know that Richard Bellman wrote an autobiography, right? The Eye of the Hurricane?
Yes. Yeah.
Yeah, it's, I just checked through that, and he doesn't really have anything to say about his preference for exact solutions or approximations. But
I think that someone else wrote about Bellman.
Yeah.
He was really unhappy with the numerical methods at the beginning. I read it in some other source. I don't remember because it was a long time ago when I was a PhD student that I read this. I can try to dig it up, but may take a while. Until then, this is the rumor, but I think it's true. He was a mathematician, and he wanted to solve these problems in a closed form. And he was very unhappy that he couldn't do that, except for a few. And a whole branch of the field resulted from that desire. So a lot of people in optimal control and operations research are studying special cases when you can actually write the optimal policy or the value function in some special form, and maybe you reduce the whole computation to computing a single threshold or something. So they realize that, oh, we can't do the whole deal, but maybe you can have these reductions to simpler representations, which are reflecting the structure of the problem. And there is a lot of work in OR and optimal control that is of this form.
Hey, Csaba, would you mind going back to your slide where you're telling us the things we can give up on and things that we shouldn't give? Oh, wait, the things we shouldn't give up on and things we should give up on. Thanks. Yeah. I want to look at this.
Yeah. So any questions? Oh yeah, like this could, like, if I kept this slide a little bit further on, then maybe Rich's question would have been clarified. With the Markov state, for the agent, you have the big red dot. That means that I don't want a Markov state for the agent. I have to also clarify that I don't think, like yesterday, there was this question whether we should keep proving results for the tabular case. I find it really surprising how often results from the tabular case generalize to the non-tabular case. So because of that, I don't have any strong opinions about this. I can't say that like beating the bush with tabular case is necessarily a fruitless exercise. It could bear some fruits that we don't expect, right? So when you're trying to improve, let's say, sample complexity result for the tabular case, like, who should care about that? Well, I don't know, because sometimes those ideas generalize. So sometimes you work out an idea on the simple case. Anyways, that's my rant about finite MDPs. That's why the finite MDPs got a green light. And the tabular method's kind of the yellow light, which is like, yeah, okay, fine. I mean, like, I wouldn't necessarily be too excited to do this, but I recognize that this can lead to some good downstream work.
And what do you mean about Bellman error being an orange light?
Oh, the Bellman error. I read upon what Rich means about this Bellman error business, and he means okay, chapter 11.6 or something like that in the book says that this is the squared TD error in expectation. That's what he means. Okay, and then he says that, well, this is an identifiability problem, and truly there is, right? So you can't estimate this quantity from a stream of experience, because you can always find two MDPs that give rise to the same statistics or whatever stream of experience you're going to have, and the Bellman errors are different for the two MDPs. So there's an identifiability error there. So I don't know whether, like, methods that I don't like the Bellman error anyways, so I don't know. But like, if you're designing a method based on the Bellman error, and the environment is really stochastic, right? So we really have to distinguish between stochastic and deterministic environments, which is another big discussion, whether we should care about ever talking about stochastic environments, right? I don't know. But if you have a stochastic environment, then you really have a problem if you try to base things on a Bellman error. Because of this identifiability, you can confuse things. But if you introduce a lot of other approximations as well, I don't know anymore. And maybe that, like, modeling the word as stochastic is like unnecessary. And I don't know. I can't you know, like if someone really wanted to get a sound explanation of why we need to think about the word as a stochastic place, I wouldn't be able to come up with one. Except that it seems to be useful, but like there is no mathematical reason that I would call it that that would justify to. Maybe Rich has some reason. Okay, Rich.
Yeah, I would offer the reason. It's not really because the world is stochastic. It's because it's part of being humble. We want to be humble, and to say that the world is unknown, we don't know whether it will go this way or that way. To say it's stochastic is a way of being humble.
Yeah, maybe. But if it has consequences like that the Bellman error is identifiable or not, then suddenly it starts to matter. In some contexts, it starts to matter, and in uncanny ways. And then I'm not sure about whether this humbleness. You could also say that, oh, the state, like the word is so big that I can never ever, you know, represent everything. Like the state space is just too big, and that's also humble. And then you say that, well, okay, I have to just work with at the level of features or observations, and I can't have an agent Markov state. That's also humble.
Okay, well, I'll go a little bit farther. We'd say it has to do, again, with the computational complexity. Right? It's easy to have a model that says, well, different things could happen roughly these probabilities or frequencies, and that's small. But if you tried to say, spell out exactly when it does each particular thing, then your agent has to be much more complex.
I know, like, but so what you're talking about, I guess, is that if you have a stochastic word, then even planning becomes so much more difficult, right? And that's exactly one reason to not to think that the word is stochastic. I don't know. It may, yeah. So I don't know. It's entirely not clear to me what is the gain by thinking, because you are just introducing a lot of difficulties. We are introducing a lot of difficulties when we say that the word is stochastic. And it's like we don't have, I know that we're talking about that ignorance is kind of like as if the word was probabilistic and whatnot, but is it really like mathematically, if I want to write the framework in which I'm studying these problems, why should I start with a stochastic formulation as opposed to a deterministic formulation? I don't know.
I think I agree with that point, actually. I like thinking of the world as deterministic and that our approximations make things look stochastic.
Maybe the stochastic approximations to a deterministic word are much easier. It's like a relaxation idea. But it could have consequences that, like, if you know that the word is deterministic, then it could have consequences. Or maybe what Rich is saying, that it doesn't have consequences. Like, because like you never know whether it's really stochastic or really deterministic. So it's like if you try to exploit that the word is deterministic, you're just like fooling yourself, because you will not be able to do that. It's like try to build this algorithm that that exploits that the word is deterministic, and if it works, it only works because it would work even if the work was stochastic. And then why not think about the word is actually stochastic, and then design those algorithms for stochastic word. Maybe that makes the algorithms more robust, but not completely buying this. I'm kind of, yeah, I'm sympathetic to this idea as well. It's usually say that on weekdays I'm thinking this way, on weekends that way, but I don't know even which way. Okay, so Vincent had a question. He's asking me whether I was thinking about working on continuous time AQR. No, I stayed away from continuous time. I mean, like, I'm amused by people working on continuous time things. And I like the ODE kind of approach if it simplifies the math. But when it makes even the math is made more complicated, then I'm not sympathetic to it anymore. So it's like, I just don't like, I guess, like, I grew out of this mindset that I like technical challenges, and I want the simplest possible problems and that we can't solve, and then just work on that. Maybe it's wrong, but yeah. So Brandon is getting into the philosophical depths by pointing out that maybe ultimately the word is stochastic. Yeah, I don't know. Like, that's another big unknown, and yeah, I don't know whether it's even relevant to the discussion. Probably.
Have you seen the people publishing like quantum RL algorithms? I mean, it might come up.
I mean, like, the quantum RL is slightly different, isn't it? That you are throwing in the power of quantum computation. I think that's what they are trying to do.
Yeah.
That's a bit different. I mean, like, that doesn't speak about whether the word is quantum or stochastic. Like, you could do the quantum computation even if the word was deterministic. Yeah. Quantum. Anyways, discounting. Anyone wants to talk about discounting? We're way over time, but why not?
Yeah, like, I find discounting useful. I figure it might be misapplied in some cases, but it really does.
Yeah. Discounting is like finite horizon episodic.
Yeah.
I think finite horizon episodic is a little bit more of an aberration of the techniques and the frameworks than the discounting case. But it simplifies certain things. And if you're not, like, if you're aware of what is missing from it, then it's okay as a first step. It's like the tabular, like working on tabular MDPs. It's okay if you know what you might be missing. Then it's okay. Like, you're just like sharpening your pencil, and for that, like, you need the simplest possible environment. Okay, take discounting. Oh, yesterday there was some comments about that average reward is going to solve all of our problems. I disagree. I mean, average reward is, it's like the continuous time stuff. It's like there is a lot of complications going on immediately if you're not making strong assumptions. So what Roshan was getting to yesterday was that you could have these multi-chain MDPs, right? That, like, you go to this part of the MDP, then like you get stuck there, and then you can get out, and like, how do you even measure performance? I guess you can work out. It's just annoying. So the problem with the average reward framework, that the math becomes quite annoying unless, again, you're willing to make strong assumptions or some assumptions which are not going to be true. But then some of those assumptions are okay if you're not misusing or abusing them, right? Like, it's if you know that your algorithm is going to work beyond those assumptions, you take those assumptions. It's because it's the quickest way to present interesting theoretical results. Then okay, take those assumptions. Sometimes we don't quite know. Like, the multi-chain case is like that. It's like an annoying subcase that if you are studying, for example, regret, even if you have, a tabular case, you have a multi-chain MDP that you can get to some part and you can't get out, and then there are multiple of these parts, then there is not a single numerical metric assigned to your policies, because in every of those parts, every of those classes of the underlying Markov chain, if you're fixing a stationary policy, the average reward is different. So now you have a vector valued average reward. It's like, wow, that's really annoying. And if you want to prove something, that you can still get meaningful results, but there are things which are really just annoying, because sometimes it just, with positive probability, you cannot avoid being trapped in any of these classes. And then once you are in that class, you can compete with the best policy in that class. Best reward, best average reward within that class. That you can do. But it's just annoying to talk about it. So people don't really talk about it because it's like, it's not really so insightful beyond just talking about the unit chain case when this cannot happen. So people keep talking about the unit chain case. So this is another example where theorists would make a simplifying assumption. They kind of sort of know that like what's beyond it, but it's just too annoying to talk about it. So we don't talk about it. But from the perspective of algorithm design, it could matter, right? Like if you were trapped in one part, or you thought that you are trapped in one part, but actually you're not trapped, then you're comparing like you might need to do things differently if you can get out versus you can't get out, right? So if you know that you can get out, then you will try hard, because maybe in some other parts of the world everything is so much better, you can get much better rewards. But if someone tells you that, oh, there's no way you can get out, then you give up. You can have like a much more efficient algorithm in that way. And you can never know what is the probability of getting out, right? So you could have a very, very small, tiny probability of getting out, a probability that maybe doesn't matter in the lifetime, but like then it becomes really ugly, because you need to talk about the lifetime of your agent. Like, what's the lifetime of your agent? It's 100 years. It's like, what's unit are you going to use? It's really ugly. It's not. It's getting beyond math. So you'd rather not talk about this.
I think those problems are problems for the theory. As an algorithm,
it's a problem.
As an algorithm maker, I just want to get lots of reward. And if there's a way that I can get there's a way I can get better reward, I would like to go there. Yeah.
Yeah, but it depends on the smallest probability. If the smallest probability is not so small, then it worth keep trying that action that never gave you any good reward. But if there is a chance that, like in 100 years that your agent lives, it's gonna get out, and after that it goes to heaven right away, then that was a good plan. It was only a bad plan if that cannot happen. So that's the problem.
I don't see that's really a problem. Not for a framework. It's a problem for the agent. The agent has a hard decision problem, whether he should do one thing or another thing. That's always true.
Yeah, you want to have a parameter-free algorithm that doesn't need any tuning based on the environment, because that makes no sense. We don't know the environment. We want to learn about the environment. We can't know the parameters of the environment. And so for every class of environment, you need a different type of agent, and that's like not really a nice solution. So I wouldn't say it's a problem for the theory. It's a problem for the problem setting, maybe. It's like, this is just too hard. Like, there is no nice solution to this problem.
Yeah, it's kind of like a Pascal's wager St. Petersburg paradox, where if you make the possibility or like the new area of the MDP you could transition to so appealing, then you can overcome any level of improbability that you'll actually make it to there.
I don't see why this is a problem.
Yeah, it is kind of an issue with the problem setting, right? Like, you can't assume that there's just this state of bliss.
Okay, I think that as a theorist, you're thinking. So maybe it's a. I mean, you can design algorithms, and then like, what can you say about the algorithms? I want to be able to say meaningful things about the algorithm when it faces problems from a given problem class or another problem class. And you give me the problem class, I want to be able to say meaningful things about it. And what I'm saying is that if you make this problem class too big, then suddenly no algorithm will look great. Like, all algorithms just look bad. And it's kind of a boring problem, but boring setting. And it's not very useful to think about it. I want useful frameworks where the framework and the problem setting can shape my ideas about how to choose between different algorithms, because choosing between algorithms based on empirical results is like even less satisfactory, at least to me, than if I'm able to prove something about these algorithms.
Well, one big thing you can say about the average reward case that you can't say for discounted case is that you can run an algorithm. It doesn't even have to be a static stationary policy. You can run an algorithm and run it for a long time and see what the average reward is. And the average reward is a measure of how well that algorithm, that trajectory was. And so you can compare trajectories and say this one was better than that one.
Yeah. So regarding the discounted reward and its inadequacy, I think people early on realized, in the theory community at least, that this is a problem. And the way they fix it is that they make it very similar to the average reward case. So you have an initial state distribution and you're starting from there, and then like you run and you discount and like collect all the discounted rewards when you start from this initial state distribution. So it's with respect to an initial state distribution, then it becomes really similar in many respects. Some of the analysis is still simpler. I'm not necessarily advocating that this is the way to go, but it's yeah, definitely you can't. I think it's not the discounted versus undiscounted case that kind of breaks the like a lot of what happens in the tabular case. In the exact case, in the exact case, you have this full ordering of the policies. There is a policy that's dominating all of the other policies. That's not the case anymore if you have a restricted policy class. So you can't rely on that properly, and you have to have some measure, and then the average reward or the total reward, like that's the same, right? Basically, like, okay, you can normalize by dividing by the number of steps. That's fine. It doesn't really matter. Is a very natural matter, and I was stunned when I was a PhD student of why people are obsessed with the discounted case, but I quickly realized that it's just much harder to work with the non-discounted case. So I was like, yeah, okay, like everyone's doing discounting, I can do discounting too. Yeah, but I agree. It's a very artificial case, I think.
Well, so when you talk about discount or reward, do you mean that we should use, not using discounting for the problem makes sense? Like let's say total reward makes more sense there. But what about agents using discounting as a proxy to help them be more stable or something like that?
I mean, like if it's part of your algorithm design toolbox, go for it. As a goal, it's a weird goal. If when people try to use discounting in practical applications, they immediately realize that they can't pick a good discount factor. I don't know how many discussions I had with people like this, and they come to me like, "Oh, you wrote this papers about a discounted reward case. Like, how do I pick my discount factor? Here's my problem." Sorry, I didn't need that. Yeah. Jenny, you were saying something? No? Okay. All right, so there was one question. What was the last line on this slide? What to give up on? It is just taken from Rich's slide. So Rich was saying that you can't have transition probabilities, you can't have expectations, you can't have value functions for the policies, so optimal value function, action value function, and so on and so forth. And yeah, like for the agent, it's like these things don't work because you can't have the Markov state to start with. So you can't just estimate transition. I mean, you can write some update rules, it's fine, but you have to be able to deal with that when you're analyzing it, that things might be shifting around as the agent is, changing what part of the big world it's visiting. Hey, Roshan.
Yeah, I just wanted to add one thing. So we are talking about this whole discounting versus undiscounted business, and sort of the convenient reason that this was introduced is to have a total ordering on policies, right? Like there is philosophically, you can talk about what it means and so on, but ultimately the reason we want it with function approximation is so that we can order policies. But in this talk, there's this idea that we don't really care about policies; we care about actions, right? And if you're just judging an agent by the action it takes at every state, you are not asking the agent to output a rule for every other state that it is not in, then that immediate problem goes away, right? And so that puts discounting and undiscounted on like a more even footing. And then Rich wanted to say something.
Well, the first reason is with discount, with average reward, you can give a rank ordering of trajectories, which
Right.
you can't do with discount.
Right. You can only do it with respect to the initial distribution if you,
which is not what we want.
which is pretty much the same thing as the average reward anyways. I mean, like, what's the difference, right? You're taking an averaging, which is weighted by time with the discounting, but okay, like you're just summing up rewards.
Right.
Yeah.
So yeah, so instead, it's equivalent to asking for a high average reward or asking for good actions in every state. So instead of saying that I want good discounted reward from some particular initial state,
can I say something? Yeah,
Yeah.
like
And talk about
something
states.
comes to mind that's I think highly relevant is this PAC-MDP thing that people came up with, which is supposed to be a way to describe how well an agent is solving the online problem, the online MDP problem. So in the PAC-MDP framework, you're counting how often an agent chooses a so-called epsilon suboptimal actions. And you want the agent with high probability not to choose many times epsilon suboptimal actions. But epsilon suboptimal is defined usually with respect to the discounted setting, which is like totally weird, like, and totally unnatural. And there is some reduction, there is some possibility to reduce, like if you have a good algorithm for this PAC-MDP case, then with some loss, you can convert it into a good algorithm for the real setting where you care about the total reward that you collect. But it's not a conversion without loss. So it's a weird thing, and I wish it didn't happen. I wish it was only regret all the time. I guess, like, I shouldn't say this. It's okay, but I think that I think it's better to design algorithms for the regret case or the total reward case. It's the same. Than for this PAC-MDP case. And the PAC-MDP, in my mind, is really what is brought to birth because of the presence of discounting. Because people were kind of married to the discounting, the discounted total reward framework, and there it's like they quickly realized that you can't, like, if you have an agent and like it starts to live its life, and time goes by, and there is discounting, then very early on there is no use of learning anymore because it's discounted away. Like nothing that it does matter, and suddenly you are in effectively a short finite horizon setting without repeated episodes. It's a nightmare for an online learning agent. I think maybe this is what Rich is talking about, that like if you wanted to take seriously the discounted reward setting, then there is no good online error metric even to compare agents, because everything is vacuous. Because you have a very short lifetime, and within that lifetime there is no hope that you will be able to learn anything useful about your environment, and then it's done. So if discounting was real, then unless the discount factor is so large, so close to one, it's like it's indistinguishable from one for any human being, then the agent is probably doomed.
Right, and I wanted to add one more thing to that, which is, so Csaba was saying that discounting is just like a nice version of finite or episodic terminating MDPs, right? They're basically the same thing. But in fact, that in itself is a different problem, right? So for example, if you actually do have a terminating MDP, then every single policy on that is going to have the same average reward, which is 0, right? And so if you want to solve a terminating MDP problem, you not only care about the average reward, but you care about how quickly you gain the average reward. So it's not just gain optimality, which is the average reward criterion, but also bias optimality, right? So if you care about solving different kinds of problems, then gain optimality is nice to have, but in many cases, you might care about bias optimality as well. And discounting is sort of one way of studying that. And I'm just saying they're different problems, right? Like it's not, you can't say that average reward is all I care about and that's everything I need. That is one thing you might.
That's what I do say. That's what I do say. And I think the bias optimality is just a good example of people getting caught up in things that don't matter. Bias optimality doesn't matter. And that's, if you worry about it, then the average reward case is technically complex. It's theoretically complex. But that's just because you're getting caught up in things that don't matter.
I guess
certainly you can read papers and they'll go on and on about bias optimality, and you know they divide into 6 different kinds. But it's
right. So I agree with you.
You shouldn't worry about that.
Yeah, you shouldn't worry about that if you care about one kind of MDP, right? So the reason that bias optimality was introduced on top of gain optimality is to have one framework that is universal, that works for non-terminating problems as well as terminating problems. And if you care only about either terminating problems or non-terminating problems, then fine. Then you can either just have gain optimality, or you can work in terminal MDPs. And I agree that you should not try to complicate the theory and deal with both of them in the same framework. At the same time, I do think that they are both interesting frameworks to work on. So I don't think one totally supplants the other.
Yeah.
Cool.
Okay.
Okay.
Right. Maybe we should go.
Thanks a lot, Csaba.
Yeah, thanks.
Thanks a lot, Roshan and everybody.
Yeah, thanks everyone for the questions.
Bye.
See you guys later.
Okay, bye-bye. Thank you, guys.